Welcome to this explainer. Okay, we're diving straight in today because we are tackling what is arguably the single most crucial and honestly kind of the most confusing concept in all of Python. If you've ever tracked down a bug where your data just seemed to magically change on its own, or a function completely nuked your list when you weren't looking, you are definitely in the right place. Our source material literally calls us the single most important concept in Python, and it is. This fundamental topic trips up even seasoned developers every single day. But don't sweat it. By the end of this session, you're going to walk away with a completely fail-proof mental model of exactly how your data behaves under the hood. Here's our roadmap for today. First, the core concept of mutability. Second, the golden rule using the ID function. Third, immutable versus mutable examples. Fourth, why it matters with functions, and finally, avoiding common anti-patterns. Section 1. The core concept of mutability. So, mutability simply describes whether an object in memory can be changed after it's created. But here's the part you really need to burn into your brain. Independent of variable reassignment. Mutability literally has nothing to do with whether you can point a variable name to a new value. It is strictly about the actual physical object sitting in your computer's RAM. This breaks down into two very distinct camps. When you operate on an immutable object, Python is forced to create an entirely new object in memory. The original, completely untouched. But when you tweak a mutable object, that exact same object in memory gets modified right there. In place, it shifts, it grows, but its core identity stays exactly the same. Moving on to Section 2, the golden rule using id. So if all this is happening silently in memory, how do we actually know what's going on? Well, we need a truth serum. And here's the absolute golden rule you must memorize. Always use the ID function to check mutability. Never, ever trust a simple print statement. Printing a variable just shows you what it looks like right in that moment, not whether it's the exact same object in memory. The ID function, though, that reveals the actual memory address. It doesn't lie. And here's how you read the results from that truth serum. If you check an object's ID, do an operation, and the ID stays exactly the same, boom, you've got a mutable object modified in place. But if that ID changes after the operation, you're looking at a brand new memory address. That tells you the original object was immutable, and Python had to go build you a completely new one from scratch. All right, Section 3, immutable versus mutable examples. Theory is great, but let's put our primary suspects in a lineup. First, let's test an immutable integer, say n equals 42. We save its ID, add 1, and while it looks like we modified n, comparing the IDs prints false. N is now pointing to a totally new object, 43. That original 42, still sitting there, totally untouched in memory. On the flip side, let's test a mutable list. Save the ID, append the number 4, and when we compare those IDs, true. It's the exact same memory address. The list just grew right where it was. Now, I want to pause for a second, because this specific flashcard from the sources highlights a massive trap. Why doesn't reassigning a variable prove immutability? Well, think of a variable in Python as just a sticky note with a name written on it. Reassignment is just peeling that sticky note off one object and slapping it onto another. It tells us absolutely zilch about whether the original object underneath actually changed. Which brings us to Section 4, why it matters with functions. This is basically a high-stakes crime scene for your code. Look at these two functions. First, add_item takes a list and appends to it. We pass in our ingredients list, water and milk. After that function runs, our original list outside the function is permanently changed. It suddenly has ginger in it. But look at the shout function. It takes an immutable string and calls .upper on it. When we print our original name variable afterward, it's completely unchanged. The function could only create a brand new uppercase string to return. It was totally powerless to modify the original string. To really hammer home why that list changed, consider what happens when you pass a list to a function. The function receives a direct reference to that exact same list in memory. It does not get a safe little copy, it gets the actual keys to the house, and that is exactly why it can permanently modify your original data. Let's wrap up with Section 5, avoiding common anti-patterns. Now that we've got the mechanics down, let's bulletproof your code by looking at the pitfalls you absolutely have to avoid. Anti-pattern number 1, checking mutability by watching printed values. Like we said, ditch that habit and always use the id function instead. Anti-pattern number 2, reassigning the return of an in-place method back to your variable. Let's see exactly why this second one is so dangerous. Honestly, this warning is a complete lifesaver. Methods that modify mutable objects in place, things like .append, .sort, or .reverse, they actually return none. They do the work to the object and then return absolutely nothing. So if you casually write my_list equals my_list.sort, you have literally just overwritten your precious data with a none type object. Poof, it's gone. Always, always call these in-place methods on their own dedicated line. As we wind down, just keep this quick reference list in your mental toolkit. Your primitive types, stuff like integers, floats, booleans, and strings, plus tuples, those are immutable. If you need to change them, you're making new objects. On the other hand, your dynamic collections, like lists, dictionaries, and sets, those are mutable. They change right there on the spot. And I want to leave you with this slightly mind-bending thought to really test your grasp on all this. We just established that tuples are immutable. But can a tuple contain a mutable object? The answer is absolutely yes. A tuple is strictly immutable at the top level, meaning you can't add or remove items from the tuple itself. But what if item number 2 inside that tuple happens to be a list? Well, you can append to that inner list all day long. The tuple is still holding the exact same sticky note pointing to the exact same list, but the list itself is mutating under the hood. Kind of mind-blowing, right? Keep experimenting, keep checking those memory IDs, and we'll catch you in the next explainer.